Good morning, Chem 20s. Our lesson today is going to be on comparing pH and concentrations within acids and bases. Many scientists have had theories on what makes something an acid. Sir Humphrey Davy in the early 1800s was the first to suggest that hydrogen gave compounds acid properties. Then, Justus von Liebig expanded the theory to say that acids were ionic compounds in which hydrogen replaced the cation ion. However, neither definition could explain why many compounds containing hydrogen had neutral properties, such as methane, or basic properties, such as ammonia. In the late 1800s, savant Arrhenius provided the first useful theoretical definition of acids and bases. His very simplistic definition stated, acids are substances that ionize in aqueous solutions to form hydrogen ions. And bases are substances that dissociate to form hydroxide ions in aqueous solutions. What I would like to do is let's take their definitions and let's actually see them in practice. So I'm just going to grab a nice lime green pen. Why not? So if the definition of Arrhenius for an acid was acids will ionize to form hydrogen ions in solution, then when I have HCl, it's gonna ionize into hydrogen ions, and again in solution aqueous, and chloride ions. Again, same rules as always. It's going to balance when we're done. So one hydrogen, one chlorine, no charge on the left, one positive, one negative, no charge on the right. Arrhenius would say we know HCl is an acid because we have hydrogen ion as a product. Let's try nitric acid, HNO3. So it's in water, it'll ionize, into hydrogen ions and nitrate ions. Again, we're going to balance this, one hydrogen, one nitrate, no charge, one positive, one negative, no charge. Again, we have proven that HNO3 is an acid because in Arrhenius's definition, it has a hydrogen ion coming out once it's in water. His definition for a base, however, wasn't about hydrogen ion. It was that bases will dissociate in solution to make a hydroxide ion. So when NaOH, sodium hydroxide, it's going to dissociate into sodium ions and hydroxide ions. Again, it needs to balance one sodium, one sodium, one hydroxide, no charge on the left, one positive, one negative, no charge on the right. Again, Arrhenius would say, hey, it dissociated to make hydroxide. That is the definition of a base. Last one, magnesium hydroxide. It would dissociate into magnesium ions and hydroxide ions. So we have one magnesium, two hydroxide. We're going to need two hydroxide, no charge on magnesium hydroxide, two positive plus two negative, no charge on the right-hand side as well. Again, because of the hydroxide, we proved that magnesium hydroxide is a base. Now, this works quite well. However, this is a very simplistic theory for acids and bases. It is extremely useful and it's wonderful in the beginning. However, Arrhenius's theory was actually modified. And instead of saying hydrogen ions, because hydrogen ions actually do not exist on their own in solution, because remember, in this solution, there's also water floating around. And so what happens is these hydrogen ions some of them bond with the water and they make something called a hydronium ion. And so this H3O plus is a hydronium ion where we have H2O and a single H positive hydrogen ion bonds to it to make H3O positive. So what I want to do is let's take the exact same example of HCl. And because we know it's in a solution with water, let's add the water into this reaction, make it more realistic because we have loads and loads of water molecules floating around in this beaker with HCl. And so what happens is in this HCl, the hydrogen from the HCl, when this guy dissociates or ionizes a little bit, it's going to join the water. And we say that this proton, and what I want us to stop and think about for a second is why do we call this hydrogen a proton? Well, if you think about it, the most common form of hydrogen in its ion form doesn't have a neutron. So if we think about it, it is a positive proton and it's surrounded by this negative electron floating around. Well, what happens is this chlorine is so like right, the hydrogen and the chlorine, it's bonded strongly together. And when we did this in the bonding chapter, we saw chlorine is slightly negative side of this, hydrogen is slightly positive side of HCl. And so chlorine pulled a little harder. And so when it's sharing this electron, more of the electron is over here on the chlorine side. So that's leaving this hydrogen over here as slightly positive. And so it's got this positive. And so when water comes around and it's moving around in the beaker and water kind of rubs up against the HCl, sometimes this proton, this hydrogen ion, right? Because it has no neutrons, so we can call it a proton. The electron's tightly held to the chlorine, and so this proton joins this water molecule, and it goes from H2O, and so if it gains another hydrogen, that would be H3O, but with this hydrogen comes the positive charge. So we're going to make H3O positive, the hydronium ion. And we're still also going to be floating around. The chlorine, right, it's now loose. And because it was unequal sharing the electrons between the H and the Cl, it gets the negative electron left with it. So it now has a negative charge. Again, you will notice, although more complicated, Arrhenius would say, you know what, we have proven that HCl is an acid because we are left with hydronium ion, and that is the new definition. An acid is a substance that reacts with water to produce hydronium ion. Again, it is going to balance when we look. So we have one, two, three hydrogens, one oxygen, one chlorine, one positive plus one negative, no charge, no charge, no charge, no charge. It's still going to equal each other. However, instead of the definition being hydrogen ion, it's now going to be hydronium ion. We are looking for this guy right here. Let's spell hydronium right. So we are looking for the hydronium ion. Very, very critical in our new definition. That means from this moment forward, we are going to define acids based on the new modified Arrhenius definition of an acid. So what I want to do is let's compare the two definitions of an acid. So here is Arrhenius's original, where we said, hey, HCl or an acid is going to ionize into hydrogen ions and chloride ions. And that works well when we're in a beginning step. However, I think we've written lots of ionization reactions or dissociation reactions, and I feel we're ready for Arrhenius's modified definition of an acid. So his modified definition is, let's put everything in there, right? We have our HCl or acid, but floating around in this container also is our H2O, our water, because that's where when you look up an acid, that's where the state of an acid is aqueous, meaning it contains water. So get the water in the beaker. Again, as things move around, and I like to show the movement of the proton. I feel it helps us out, especially when we go on to grade 12 and these get a little bit more complicated. So I like to show the movement of the proton. So the proton, the hydrogen ion, is going to break the bond with HCl, and it's, depending how it reacts in the beaker, it might rub or contact water in the right way, and this proton is going to come over and it's going to now join with the water, and we're going to make hydronium ion. Again, that's going to leave chlorine off on its own along with the negative charge. Therefore, we're going to write this new equation. In both cases, we proved HCl was an acid. However, from now on, I really want us to be using the revised definition where we are talking about hydronium ions. Well, for practice, why don't you pause the video and I would like you to prove for me the example we've already done using nitric acid. But instead of proving it with the original theory of Arrhenius, I would like you to prove it with this new modified theory. I want you to make sure you are producing hydronium ion. So when I take a look here, the other thing in the beaker floating around is going to be water. Again, my acid has a proton that is going to be free and it's going to move over to the water. When H positive, my proton joins water, I am going to make H3O positive. And this time I have NO3 left by itself. And again, it's got attached to it a negative charge because the positive went with the proton, but the negative is still back here with the NO3. And so if I look at this, I have 1, 2, 3 hydrogens, 1 oxygen, 1 oxygen, NO3, NO3. And if I look, 1 positive, 1 negative, no charge, no charge. Again, I know this is an acid because based on the new definition, it has a hydronium ion. Therefore, based on Arrhenius's modified definition of an acid, HNO3 is an acid. Well, Arrhenius's modified definition of a base actually doesn't change much. He now says that a base is a substance that reacts with water to produce hydroxide. Now, in our most simple example, and that's where we're going to start, okay, I have sodium hydroxide. Because it's reacting with water, I wrote it as aqueous. Because magnesium hydroxide is reacting with water, I wrote it as aqueous. So I'm looking at the most simple examples right now, those examples that already contain hydroxide, because right now that tends to be the definition of a base that we know. So in this example, again, now that it's dissolved in water, right, reacts with water, it's going to, again, dissociate to produce hydroxide ions. So think about how it's made, cation, anion. So it's going to dissociate into sodium ion and hydroxide ion. Because it produces hydroxide ion, Arrhenius would say sodium NaOH is for sure a base. Same thing for magnesium hydroxide. It's going to dissociate into Mg2 positive and OH minus. But again, 2 hydroxides mean I need 2 hydroxides. Using his definition, it reacted with water, hence the aqueous. And because it produced hydroxide, and in this case, 2 hydroxide, right, we know for a fact that Arrhenius would say that this is also a base. Okay, well, let's take this a step farther, and now let's use the pH scale to do a comparison between pH and concentration of ions. So most of the time when we get to grade 11, we have used the pH scale a few times, but I'm always shocked at how nobody has ever questioned, what does pH stand for? What is pH? Well, pH is actually the potential or the power of the hydrogen scale. Now, ideally, if you want to, because we just revised the definition, want to say it's the potential or the power of the hydronium. scale or the potential of the hydronium ion, that would be fine as well. So what I'm going to do is I'm going to get rid of my pen for this. And you will see here that you have a pH scale. There's no surprises. Our pH scale goes from 0 to 14. You already know that it is possible to have a pH less than 0. It's also possible to have a pH greater than 14. It just happens to be not a very common occurrence. Okay. Well, in the middle of this scale then would be 7. And 7, if you remember from the previous lesson, is our neutral point. So a perfect example of this would be distilled water or pure water. Anything below 7 would be considered acidic. And so the closer you get to 0, it's becoming more acidic. So it's becoming a stronger acid properties. And then the same thing on the right-hand side, the closer you get to 14 is going to be the more basic you're going to become. So 14 is way more basic than a pH of 11. pH of 1 is way more acidic than the pH of 4. As we go away from neutral, they either get more basic or more acidic as we're looking at this table. Now, we're going to use this table, and what I want to do is I want to compare pH with hydronium ion concentration. And there is a very direct correlation between pH and hydronium ion concentration. So I've got my same table as before, my same pH scale as before, neutrals in the middle, left-hand side below 7 pH will be acid, greater than 7 will be a base. However, what I want to do is I want to attach the hydronium ion concentrations. Now, when you look at these, you are going to see that these hydronium ion concentrations all have a base of 10. So they're in scientific notation. Now, I want you to think about this. Since the square brackets stand for concentration, when we are looking at these concentrations of hydronium ion, remember, we are thinking in moles per liter. We've got to get our brain wrapped around concentrations. So because I know some of us struggle with scientific notation, what I would like to do is I would like to take a few of these numbers and put them into a real number. So if I take a look at, let's say, 10 to the negative 7, water, neutral. This number in a real concentration out of scientific notation is actually 0.000000001 mole per liter. Well, 4 then times 10 to that negative 4 is actually 0.0001 moles per liter. Again, a pH of 0 is 10 to that negative 0, which actually, if you tried it on your calculator, is just a 1. We'll also do a 10, so that's 10 to the negative 10, or 1 times 10 to the negative 10, so that's 0.00000000001. And we'll do the last one. 14 pH is hydronium ion concentration of 1 times 10 to the negative 14. So that's 0.000000000000001 moles per liter. Very, very, very tiny number. But if you think about it, on this scale, here are my acids, here are my bases, right? Basic over here, acids over here. Well, we would expect the concentration of hydronium ions, the substance that tells me that it is an acid, we would expect these concentrations to be stronger over here with a lower pH where we know the acids are. We would expect these concentrations of an acid, hydronium concentrations, to be extremely weak, if not non-existent, over here by a base, because why would a base have any acid properties? So it's not a surprise that this number is so extremely small, because bases would probably not have many hydronium ions because hydronium is the definition of an acid. Now, if we take a look down here, it says, acidic solutions are explained by the presence of hydronium ions. The higher the hydronium ion concentration, the more acidic the solution. So the higher my hydronium ion concentration, the farther I go to the left where my lower pH is, right? Higher, stronger acid, smaller pH, the higher this concentration of hydronium ion is going to be. Now, I want to do a comparison on this. So let's take this a step farther. So if I have a pH of 4, that's 0.001 moles per liter. Well, if I have a pH of 3, that's 0.001 moles per liter. If I was to compare these two pHs, so I had a pH of 3 and I had a pH of 4, what can we say about my pH of 3? Well, if I take a look here, I can say that for every step on my pH scale, so a pH of 3 is going to be, well, compare these concentration, 10 times more acidic because it's got one less decimal place. So pH of 3 is 10 times more acidic than a pH of 4. For every pH spot we move on this scale, it is 10 times more acidic. Therefore, when I go from a pH of 8 to a pH of 6, well, a pH of 7 is 10 times more acidic than a pH of 8. A pH of 6 is 10 times more acidic than a pH of 7. Therefore, when I go from a pH of 8 to a pH of 6, this is going to be 100 times more acidic. And I'll prove it to you. If your pH of 6 is 0.000001, right? Times 10 to the negative 6. And your pH of 8 is 0.00000001, right? 10 to the negative 8. The difference between these two is 2 decimal places. That is, pH of 6 is 100 times more acidic than a pH of 8. I know for some of us it's going to take a minute to get our minds wrapped around scientific notation. And that is why I tend to pick an occasional one. And I like to take it out of scientific notation and put it into a real number so that it's easier to compare. Okay, well, the other thing we can do is let's compare the pOH scale. Now, you have never heard of the pOH scale before. The pH scale everybody tends to love because we've done the pH scale many times in previous science courses. The pH scale was the power of hydrogen or hydronium. The pOH scale is the power of hydroxide or the potential of hydroxide. The interesting thing about this scale is that when we look at this scale, it is the exact opposite of the pH scale. We'll notice that 7 is still in the middle, which means 7 is still neutral. So whether it's the pH scale or the pOH scale, the middle number is our kind of connection. 7 is still neutral. However, while in a pH scale, numbers less than 7 mean acidic, in a pOH scale, values greater than 7 actually mean acidic. So the greater the pOH value, the more acidic it is. So a pOH of 14 compared to a pOH of 12, a pOH of 14 is way, way, way more acidic. This is also true when it comes to basic. Whereas in a number greater than 7 on the pH scale is basic, a number less than 7 on the pOH scale means basic. So I always like to do this. When I have to answer a POH question, I think of it in terms of pH. And if I look and go, okay, the POH of a value of 1, is that acidic or basic? I go, okay, if this was the pH scale, a value of 1 would be acidic. Therefore, on the POH scale, it's going to be the opposite. So a value of 1 is actually going to be basic. Hope that cleared it up a little bit. So where the pH scale is the concentration of hydronium, the POH scale is going to be the concentration of, and you can see it in here, hydroxide. So again, it works exactly the same way when it comes to scientific notation. 10 to the negative 7, if that's a POH of 7, it's 10 to the negative 7. So that is going to be 1 times 10 to the negative 7, which is 0.0000001. Again, POH of 10 or 10 to the negative 10 concentration will be 0.00000000001. And a POH of 14, which is a hydroxide ion concentration of 10 to the negative 14, is 0.000000000000001. 4 would be 0.000001, and of course, POH of 0 has a concentration of 1 hydroxide. Now, the interesting part about this is, again, when we're talking bases, and that's when we use this, right? Because this is hydroxide ion concentration. Again, on this scale, acids are on the left, bases are on the right, and we would expect that when we get more basic, we would expect to have a higher concentration of hydroxide ions in moles per liter compared to when my substance gets more acidic, right? So my pOH is greater than 7. When my pH is greater than 7 and it gets more acidic, we would expect to have a very low concentration of hydroxide. Because Arrhenius said, the presence of hydroxide tells me it's a base. So I would expect a very, very tiny concentration of hydroxide in acids, and I would expect a much higher concentration of hydroxide in bases. Basic solutions are explained by the presence of hydroxide ions. The higher the hydroxide ion concentration, the more basic the solution. So let's take a look at this by comparing the two side by side. So I have my pH scale and I have my pOH scale. And you'll notice, other than 7 in the center, neutral, these guys are exact opposites of one another. I know you're comfortable with pH going from 0 to 14, this side then being the acid side, this side being the base side. But I also then want us to compare the hydronium concentrations compared to the hydroxide concentrations. Again, at 7, they're going to be equal because if you are neutral, right, your pH is 7, your pOH is 7. They are equal. Not hydronium ion is not winning, hydroxide ion is not winning. You'll notice their concentrations are exactly the same, whether it's hydronium or hydroxide, because this is a perfect mix for water, right? It's got properties of acids and bases. They cancel out, so they are going to be neutral. Again, we're seeing this concentration of hydronium is equal to the concentration of hydroxide. All I'm doing here is using my symbols. Square brackets means concentration. Again, we're comparing hydronium hydroxide because it's neutral, dead in the middle. Again, it means both of their concentrations are going to be 1 times 10 to the negative 7, or both of their concentrations are going to be 0.000000001 moles per liter of hydronium and 0.0000001 moles per liter of hydroxide ions. Well, let's look at why this works the way that it does. So our original definition of, says Arrhenius, could be applied in this case. So we could say, hey, we have one water molecule, and our one water molecule, if it dissociates into ions, and we say to ourselves, but it's molecular, Mr. Kemp, it doesn't want to. And I agree, it doesn't. And so it does break up, but it doesn't break up in enough that if I used a conductivity tester, the light would turn on. So are there some ions present? Yes. And down here it says, 2 molecules out of every billion molecules of water in a bucket of water will ionize to form hydronium and hydroxide. So it tells you it's a small amount, but it does ionize that little bit. So using our original definition, right? Water will just ionize into hydrogen ions and hydroxide ions. I know water is neutral because it's got both hydrogen properties and hydroxide properties, and we saw that's the neutral point on this. Well, now that Arrhenius revised his definition from hydrogen, we're going to revise ours as well. So in this case, we're going to need 2 waters. When they dissociate, they're going to make hydronium ion and hydroxide. And it's hard to see how it works by writing it as 2 waters, so I like to show it. So I have 2 waters floating around, right? Because I have billions of waters floating around in a bucket. And they're eventually going to bump or rub or something in the bucket in a way in which one water is going to give a proton. So this water is going to give a proton to that water, and that's going to form us an hydronium ion. Well, if this water loses a hydrogen, it's going to be left with OH. If the positive leaves to join this water, then the negative is going to stay, and that's going to also leave us an hydroxide ion. So instead of saying, hey, water is made up of hydrogen and hydroxide, remember, in a bucket, we have millions of molecules of water. And so it's one of those where if they bump or rub or touch in the appropriate way, then the proton is going to move and we're going to end up with hydronium ions and hydroxide ions. Now, to make you feel better, yes, 2 molecules out of every billion molecules of water go through this. If you want to think of this in percent yield, that means this occurs less than 10 to the negative percent, less than 0.0000001% of the time is this actually going to occur. So this is a very small percentage. However, if you think about how many molecules of water are in a beaker or in a bucket, we're talking about billions. And so it does occur in there. So the last thing I want to do is, if I was to, and let's look on our pH scale because you guys are much better at the pH scale. So we know we have a pH of 3. Okay, we know we are dealing with an acid here. Well, if we're dealing with an acid here, we have to look at the whole thing. That means that we have hydronium ion concentration of 1 times 10 to the negative 3, but that also means we have hydroxide ion concentrations. And most of us would go, why are there any hydroxide ions in an acid? We just said, hey, we have an acid. It's got a pH of 3. Why would we have any base properties? But again, I want you to remember, whatever acid we choose, HCl, the state is aqueous, which means water is dissolved in here, which means we have some tiny little bondings of water with other waters that we just proved where there are going to be some hydroxide ions floating around. Now, there's not many, right? When we compare these, hydronium completely wins compared to hydroxide. And the stronger our acid becomes, the significantly less or minuscule the hydroxide concentration is going to be. So although in every acid there are some hydroxide ions, they are so tiny compared to the amount of hydronium that they don't even register. And our acid wins because all those hydronium ions take place. Same thing with bases. Again, I'm going to pick a base here. So I have a base with a pH of 13, right? It has a very high hydroxide ion concentration. It's got an extremely low hydronium. Ideally, why does it have any hydronium ions if it's a base? It's because water is present and water could dissociate and react and make, right, hydronium and hydroxide.